as we already said, I was trying to mimic as closely as possible the description of this talk. I think I did quite well, except for one detail, and that is it's very practical. So I don't have slides. All I have is a notebook. That means I execute Python while I talk, which is a little bit brave, I think. I don't know. Maybe it's silly. We will find out. And I also have some hand drawings. So this is my hand drawing. It gets a little bit worse, but not a lot. So bear with me a little bit. So who already knows a lot about machine learning? So that, are you, yeah, okay, not very many. What about neural networks? Okay, also, why you're here in that introductory talk. So anyway, so we will find out. So no, one more question. Who's a programmer? Perfect, so I'm a programmer as well. And I always thought like I should start from something that we all know, that we're all familiar with. And this is typically my daily work, like the first box up here. And that is, I get some requirements of a program, how it should behave. And then I'm the one here in the middle. I'm the human programmer, sort of. And then I hack some code, and that code represents the model that's on the right here, right? So I get the input, I do my work. There's something that you could, by some justification, call a model, namely the program, and then it runs, and then it does stuff. Obviously, I'm pretty certain that you already know that machine learning like turns this around a little bit. So you also want to get a model, something that you can use to do something in the end. This thing here on the right side. But the way you approach it is very different. So what you do is you, at least in supervised learning, you supply some sort of algorithm, some strategy. You supply it with some input and matching output. Like this drawing here, as an example. Say you want to train this thing here in the middle, and then you want to give matching pairs of things like, this is a pig. I know it's a good joke, but I'm not making this up. I don't know. Probably it's a pig. And then you like feed in those two things, like the input and the output, that pair. So the classifier now knows, okay, a pig looks like this, and then you feed a second pig. Hopefully this is a second pig. And then you also say, this is a pig. And then like a small child, well, not technically like a small child, but like learning like a child would do, the system, with each sample that you provide it gets better at recognizing pigs. And then also with cats, for example. This is a cat, and this is a cat, and you feed those two pairs into that classifier, and then this thing will learn to classify certain pictures to certain labels. This is, well, I did this drawing like 20 minutes ago, so I think it's not worse than the other thing, but I don't know if that's good or bad, but anyway, so this is just one version of machine learning. So there are 3 types of machine learnings. The first one that I just described is supervised learning. They do the most work, well, like you have to like guide the system more than with the 2 other types. And as I already said, you provide pairs of input and output and you train the system. And I named 2 strategies here, namely neural networks and decision trees. There are many more learning strategies for supervised learning. These are just 2. And this is just for the overview. So we will be talking about supervised learning and neural networks for the rest of the talk, but just to give you an overview. So there's also unsupervised learning, and unsupervised learning, you have to give the least guidance. You just have the algorithm, you tweak a little bit, few parameters, and then it tries to reveal things you didn't know were in your data set, like this PCA thing, it reduces dimensions, like you have, say you have a lot of dimensions and some of them are not relevant, some are, I don't know, correlated to each other, then PCA reduces this. Or there's also clustering, and there's also more. And clustering tries to find similarities, like you would do, I don't know, in a meeting, where you cluster certain topics. And it does it fully automatically. So this is the one where you give the least guidance. And then there's also reinforcement learning, where you what's that word? Experience. When you stand so close to it, then experiences, by making experiences. Okay, so the deal is what you give that system is you give a reward system and tell the system what is good and what is bad. And then what such a system can learn is, one of the famous examples is play Atari games, and you just tell it, if that score goes up, it's good, and if you die, it's bad. And that is the reward that you give to the system, and the rest of the system learns by playing the game over and over again. And such a system that at least partially relies on reinforcement learning, actually, like this year or last year, it has beaten like the #1 in Go. And this was something that was thought to be impossible, like a year ago or 2 years ago. No one would have believed that. So this is just to give you an overview. And we are in this bluish thing up there, supervised learning. By the way, if there's anything you want to ask, and I understand you, I will answer. There's also something. I stole this visualization here. So there's also something like, what is artificial intelligence, and what is machine learning, what is deep learning? And I not only stole this thing, I also think it's bad. It's not a good visualization, but it's the best that I could find, because there is no clear separation between those anymore, at least from my perspective. So it started out in the 50s as artificial intelligence, then machine learning was something thought of like very interesting, and then deep learning, something we will come to at the end of the talk, was like a specialization of this machine learning. But now it sort of turns around that all things that we call artificial intelligence, like the modern stuff, is actually deep learning. So it's strange. So every time I try to come up with like a Venn diagram or something where I try to draw on relations, it's always a mess. So I at least tried. So. Okay, as I said, what we have here, it's a notebook. That means in each cell you execute some Python code, but no worries, you don't have to understand that. Because the main point here is we make it run and see something. So this is all just imports. It's real code, so I actually had to run this up front. And we can make changes if you want me to. If you say change this and it makes any sense, I will do it. Probably I would just say it doesn't make any sense, so, but to save me. So what we have here is a very classic example, very, very boring, and is we are trying to write a classifier for iris flowers. I don't know. And they look like this. You scroll a bit. Oops, where is it? Okay. I don't know, they don't look like this. So, sorry. I have to click on the link, unfortunately. Sorry. I will do it now. Not so good. I'm glad that I have this thing locally. I can't show you an iris. Is anyone able to like envision an iris? Like, how does it look like? It's just a flower, I have no idea. So it has like the leaves and stuff. And just imagine, I'm sorry, no internet, no iris. Just imagine this is an iris. It's totally not. So any botanical people in the audience? No? Oh, yes, you are? Okay. Do you promise to not say anything? So it's an iris. It's this is an iris, actually. It's an iris yellowica, I don't know. No, I'm making this up. But the important part is what we have in that data set is we have the sizes of this thing here, which is called the petal. Like I thought that is the actual flower, but it's just a part of it. And then there's the greenish thing here, the sepal part, or sepal, I don't know how to pronounce it. And that is the part that wraps around that beautiful thing. And what we have is we have the length of this thing, and the width, and also length and width of this thing. That's all the input that you have. That's the so-called iris data set. And if you plot that in a scatter plot, I think it should be visible, sort of. We have a lot of scatter plots because we have 4 variables here, but we only at each time plot 2 of them. So that means in this example, we have the length of the sepal and the width of the petal, and so on and so on. So how many of them do we have? I don't know. You can count yourself. Probably it's 12. Not sure. Probably yes. And now for each individual data point that we have 150. That means 50 per category. We plot 1 point. Like this is the red one. One sort of iris, another sort of iris, and still another one. And you see that red thing is pretty easy to separate from the others, and they are sort of mixed. But it also varies a little bit depending on what variable you take here. So this is just something that I typically do to get an idea of the data set, just to get an intuition. This is just, I don't know, this is more art than, I don't know, engineering. Look at it and then sort of get an impression. So what do we do now? So we approach this with neural networks. And a neural network consists of single neurons. And I hope it fits. Sorry. Still not. Toolbar. OK, good enough. Now it fits in the picture. This is a neuron. Of course, it's not really a neuron. It's not even close to, well, it's inspired by the neuron that we have in our heads, but actually it's people who are good at neuroscience tell me this is not even close to what a neuron does. But this is like the 1950 view of a neuron. And how does it work? So you have a bunch of inputs called x1 to xn, and you multiply them with weights, weight 1 to weight n, and you have an additional constant weight. Well, constant in the sense that you just add it to it, and then you sum all that up, and you put it through an activation function. That used to be just like a step function. So up to a certain point, it didn't react at all. It stayed 0, and then at a certain point, it fired like a 1. Like a neuron was, well, they thought a neuron would work like this. And this is the formula for it. Does anyone know what kind of formula that is? Well, if we were drawing that, how would it look like? Let's say the activation function is just, let's disregard the activation function. Well, what kind of formula is that? Is it too easy? Is it too hard? It's a linear function, right? It's a line. So that means, well, just intuitively, with one neuron, you can just draw a line. And again, this is not technically 100% accurate, but if you looked at this, at these planes here, and then we would consider how many lines, if I just have lines, how many lines would I need at least to have a halfway decent separation of these three categories? How many lines? 2? At least 2, right? So one might go here, and then the next one might go here, right? It wouldn't be perfect. You probably would need more lines to actually have a very good separation at this point here, because the blue and the green ones are mixed. But this is, again, an intuition. If you were to actually come up with a good neural network for this, we would have to think of how many neurons do we need, and 3 or 2 actually is a good measure. And it's obvious, right? That's what I did. So that's a question we were answering. Now, as I said, one of those neurons is not powerful enough. Someone showed in the, I don't know, maybe it was in the 60s, someone showed that such a single neuron can't even approximate an XOR function. It's not possible. You just can approximate something like an AND or an OR, but not XOR. That means it's not powerful at all, but combined, it makes a lot of sense. So that comes to this approach. So we're taking the whole neuron here, single neuron, and then we organize a set of neurons in at least 3 different kinds of so-called layers. The input layer is just there to receive something, receive input, like the 4 inputs that we were seeing, like the dimensions of the flower leaves of this iris. Then we have output neurons on the right side, and these are there to actually spit out what we want. So if you would just having like a linear function, then we would have like a continuous output, but typically you want something like, at least something like a likelihood for each of the categories. And that's what, in our case, will do the output layer on the right side. And this thing in the middle is the thing that does the real work. Like, if you imagine that visually, it draws those lines between the categories, like in those scatter plots. So the first thing is there to actually have this accessible to the network, the input layer. The output layer is there to encode it in something like categories. And the thing in the middle, it draws the lines here. Of course, this is technically not 100% correct, but to get an intuition for it, it's totally fine. Okay. That's the idea. This is done, it doesn't matter much. This is done in Keras, which is a front end to TensorFlow. The model runs in TensorFlow, which is total overkill, because we have 3 neurons here. You don't have to look at the Python code at all. Can you read that from the back? Can you read that? Good or bad? Good? Okay. Maybe I can zoom in one more. No, I can't. Sorry. Very sorry. No, we have to leave it like this. So the important thing is this here. So you see that drawing up here, and what I need to do now, I have to like translate that into Python code. And this is Python code. This is our input layer. This is the complete input layer. It has 4 inputs for the 4 variables. The rest you can just disregard. And then we have a so-called dense or fully connected layer, and I will show you in a minute what that means. And we have 3 neurons in it. We could try it with 2 neurons, because we saw it might also work. Maybe not perfectly, but shall I do it? No, I'm afraid. Maybe do a little bit later. So we have 3 neurons, and then this is all just like code. It tells us we have 15 parameters to train. Oh, by the way, why 15 parameters? I didn't quite explain that, right? So, I have to go back up again. So, what is fixed in this thing here, in this neuron thing, is that you have these inputs, and it's also fixed what this activation function is. But what is not fixed, what is learned by the learning strategy are those weights here. Weight 0 to weight n. And that means that is the parameters of the line. Like, how is it drawn in that area here? I think it's obvious, but maybe I just, because I can, I'm drawing it here. Say, this is the first line. And it has a certain slope, it has a certain offset, and this is encoded in the weights. And this is what the algorithm is going to learn, right? There might be another one here, right? That might be quite reasonable already, except that there are no lines, but almost. I did my best here. So, like the slope and the offset, which is like a bit more visual or intuitive for these weights, this is what the algorithm has to learn. And since, scroll again, since we have 3 neurons with 4 inputs, that makes 12 weights to learn, plus 3 constant values, the weight 0, like the offset. That makes it 15 values to learn. So the next thing I'm doing is actually, well, I make it train, so I teach it by providing these samples and then trying for the learning strategy to determine those values. But first, there's a visualization for how the network actually looks like, and it really looks like this. So this is the input. It takes continuous values because these are the 4 sizes, the size metrics of the flower. Then each of those input neurons is connected to these hidden neurons, and that's why it's called fully connected. Fully connected means everyone with everyone. Another name for that is dense. So Keras calls it dense, but it's the same as fully connected. And then also this last layer technically also is a fully connected layer, but it works a little bit differently by having a certain activation function that allows it to output likelihoods, or something that we can interpret as likelihoods. Namely, this first output would be how likely is that this input here belongs to this category, and then to this, and then also to this. And they all always add up to 1, like in this example. So in this case, if I use it as a prediction mechanism, the predictor would be very, very sure that this is category 1. I think that's also a realistic example. It really is category 1. So this is how the network would look like. And we have 2 stages. Now, the first stage, we train this thing, because the weights are just random. When we create that network, the weights are just random. The variables, they go somewhere here, and the lines, they just go somewhere. So even though the network is set up, and that is called the architecture, the important parts, namely the weights, they're not set in any reasonable way. And that's what we're doing now. Now we are passing through all these values and try to train the system. And prepared that. Sorry, I have to skip it for a moment. Just want to show it. Oh, this is all still preparation. Here's the training part. And I might go back in the notebook, but maybe not. What are we doing now? So the model is like the definition of the network, and now we feed in some input data with matching output data. This is arrays, so it's vectors. And then how many times are we doing it? We're not doing it just once, but 500 times. And there is no rule how many times you do it. Typically you do it until you get the impression it's good enough. There's a lot of hand waving, and it's really an experimental science, if it is a science at all. I read some scientific papers, even though I'm not a scientist at all, and they're all like this. We tried this out, it worked. No idea why. Yes?
My impression would be that you would try that this at least depends on the number of training input and outputs you have, right? So isn't this dependent on the size of your...
Sure. Totally, yes. So there are some indications. So the question is, isn't this dependent on some of the things that I put in? And it's totally yes. So it totally depends on how complex is the model. It's very simple. It's almost stupid. And then how many data points do you have to feed into it? And that's true. So 500 iterations over those data sets might be too many, but the good thing is it's very fast. So typically something like this could take on a GPU, like a very, very powerful thing, it could take hours, maybe days. But this thing, it will take seconds. And you will see the training thing, if I set it up correctly, and I think I have, because I don't rely on the internet here. Then before I run this, and you see something will happen here, what we did, we split the data that we had. And if you're at all into machine learning, you probably know why, because we want to know how well did the algorithm actually learn the data. So we save some of the data later for testing. And then again, we also do the testing while we train. So even while we train, we get an impression, how does it work with data it has never seen before? That's what I'm doing now. And you see it's very fast. Each iteration, even on a very cheesy i5 here, it takes just a second. I have to be quick here. This is that's really strange. I think I didn't reset the model properly. So you see the accuracy, how well does it behave on your trained data? It's just flat 1, and that is totally cheesy. It's not possible. So probably I trained this before, and then I forgot to reset it. And I'm trying to reset it now, and then we get a second run here. It should be fast. Okay, Should be reset now. Reloading it, because this is not a curve that you would expect. You saw immediately that I thought there was something suspicious. This is also intuition, but it's not like I'm a brilliant person. It's like very trivial. And this sounds and looks much better. So what you see here, we are at iteration 160, we have 500. It's very fast. And you see that the accuracy actually describes, in this case, how many of the irises that are fed in, where I know the actual result, how many of them does it properly reproduce. And this is the training data. So it has perfect knowledge. But this is not actually something that you're typically interested in, but this is actually what you're much more interested in, namely, how well does it work on data that it has never seen before? And this also goes up, but strangely jiggling, and that is in largely due to the very, very small data set that we have. Like, any statisticians in the audience? No one? Or are you afraid to? 150 data points? I mean, and you split it into like smaller parts, and then you train with 90, and then you might see that that might not even be statistically valid at all, but did it like finish? I think it finished, but the board, it doesn't update properly. I don't know. It's not a good day for demos, but it's not too bad. So you see it goes up all the time, and this also looks okay-ish. And then once we've done that, we trained the system. As I said, not like in programming, where you have a unit test and you make it run, and then you know like how it should behave, and then you look at the code maybe even. You do something like a code review. We can't do it here because we can't look inside the model. But what we can do, we run a set of data sets that we didn't use for training. But first, we run a set of we run a test on the data sets that we used for the training, and we get this accuracy. That means it's 98 of the samples that we provided with, it can properly predict. It should be able to do something like close to 1 in this example, but maybe the model was too simple or something. And then the more important part, we feed in the test data, like the data that we saved for trying how it performs on data it hasn't seen before. And this is 96. And it's pretty good. It's not perfect, especially given that the sample size is quite low and the problem isn't too hard. I don't know, maybe I would even be satisfied if it was a real problem. What could we do to improve that? I mean, if you said, okay, 96% accuracy, it's not enough for me. What could you do? Just to check your intuition. Yes?
Maybe just use more nodes. I mean, you used make it bigger, maybe that helps.
Yes. So we could increase the size of the network. I think I used 3 nodes. And we can do, I don't know, 10. Shall we do it like super heavy? We'll do it. 10 is still like nothing. And even if for toy problems, you might have to wait for hours until you get the result. So if you're used to like programming and do it interactively, then that's bad news for you, at least for me. So we're trying it again. It's still very fast. It can get very slow at a certain point, but it's still very fast. Let's have a look. Again, those metrics. That looks better. So this is something like you see that the model actually stopped, or it looks like it stopped doing something reasonable at step 100 maybe. That's the accuracy of the training data, and this is the validation accuracy, and it also like stayed on this level after step also 100. It doesn't get very much better, but you can still try it. Evaluate it again. It's same. So it could be we would have to run like more batches. It might be that we're actually overfitting. So there's a lot of things that could go wrong here, but that would be rather a talk about machine learning than neural networks. So because of that, I want to go to some other stuff also, because it was advertised in the abstract of this talk. First of all, just as a side note, this is like, it looks like, of course, well, how should I put it? The example, of course, it's not a real example, but the code that I would write to tackle a real example, it's the same. So in the end, what you do, you have trained your model, you've evaluated it, it looks okay-ish, and then in the end you would save it to a certain file, and then you might deploy it to some, maybe to your own service, or you could also deploy it to the, at least in that case, to the, not quite sure if I'm allowed to say that, but why not? So the Google machine learning cloud, it can take TensorFlow models, and then you can use it to like make predictions on it. So this is a very simple example, but you can take this idea a little bit further. And then the next step, and this graphic I stole, that's why it looks nice. It's from Jan LeCun, one of the stars of that area, and he explains what does it mean. So what well, in our example, we really didn't have this much, but in classic machine learning, you would have a person doing this, like thinking of the features that you have, like these metrics of the sizes of the leaves, and then try to find out what is relevant, and then how do I have to encode that, and then, I don't know, how do I manipulate that? And that is something that's totally, it's a lot of work. Like after cleaning data, it's like the most work-intense part. And the idea is that now, these steps where you like extract the features, you normalize that stuff, you get the idea that each of these things that happens until you actually do the retraining, you also let this learn, or you also train a system on that. And that system, it learns how to encode those features and what features are relevant and what are not. And that's why it's called deep learning, because you have many steps, and each step does a little bit of feature recognition, it does a little bit of more abstraction of the features, and then eventually you again have something like a classifier. And practically, or most of the time, or let's say all of the times I saw this is done by neural networks. It's not like totally necessary, but that's all I've seen so far, only neural networks. Question to the audience. Anyone else having seen anything else in deep learning but neural networks? No? Oh. I would have loved to get an example of something else, but okay, good. Maybe not so good, I don't know. And this is one other drawing to give you an idea what it might do. So again, I've drawn a bear. I know it's a bear. And what I want to send it to layers, or well, rather blocks in that case, of deep learning parts, components, and then eventually I want the system to spit out that as a bear. And as described before, like when I screw up, these things here are these, and this final thing like the classifier are these. And they consist of different types of networks, and these ones, like the green ones, are very special because they work like filters. Anyone ever used Photoshop? Filter kernels? Like blur kernel or sharpen kernel? It works like I don't know how to describe this mathematically or if it helps at all. It's a certain matrix, and then you apply it to a picture, and then it does something to the picture. And what it does, or how that matrix looks like, that is the variables of the network that is learned by the network. And just to give you an intuition, what gets done to the bear with each of these blocks, I know that's not a bear. That's obviously a dog. But these are the operations. I'm not quite sure if you can see it in the back or if you can still see the dog. These are different types of operations on that dog that some look like edge detection. And then there's also a kernel for edge detection. And then there's a kernel for blurring. And then there's a kernel for sharpening. And the neural networks, in those early layers in the deep learning process, tries to learn what is interesting in that dog? And with each layer, this is just one, you might have 100 or maybe 150 layers. With each layer, it gets more abstract. Like it does a little bit of filtering, you still see the dog, and eventually you just see eyes, might see a snout or something, if the training goes well. And that's the idea. So you try to like encode the meaningful features of that dog into more and more output things. And I think I have this, not quite sure if it's a good graphic, but at least it's not one of my drawings. So the idea is you take that large picture and you make like the features that you get from it. Eventually, you want to have a lot of features like extracted from the image, and this represents like a lot of features. And then the first thing in the large image, there are no features. This is just pixels. And that's the idea, that it should work. I have a few examples, and I think I have 10 minutes. So just to give you an idea how well this could work, I have taken a very standard architecture that's called VGD. I don't know why it's called VGD, no one knows it. And it's trained, pre-trained, and I just use it as a pre-trained network. It's trained on a data set called ImageNet. Some people collected like a huge sample of data, and they took pictures of a lot of bears, they took pictures of a lot of dogs and cars and stuff like that, and then they fed it into the system, trained it, and now first what we do, we give an overview of the network. I didn't define it. It's a standard one. It's pre-trained and preloaded, and you see each of these is a layer, and this is the number of totally trainable parameters. We had 15, and this is 138 million, I don't know, a lot. Also almost 140 million parameters that are trained. And then I took this beagle here. I know it's a beagle because it said so in the title. I don't know, I wouldn't have like guessed that. And then you can feed this thing into the model, and it tells you again with a certain percentage of like how sure it is. It tells you with 30% accurate, or not accuracy, sorry. It tells you with 30% like what's the word that I'm missing? Probability. Thanks. I used it before. It tells you that's a beagle, and that's totally right. It doesn't look like a lot, 30%, but it's more than all the others, all the other probabilities. English foxhound, I have no idea how that looks like, 26. It's quite okay. And then a friend of mine has a cat. And where's that cat? Oh no, I don't have internet, right? Not good. So that's a cat, and it tells me it's Egyptian cat, actually something else, but very close. Then I have squirrels, that chubby one here, more squirrels, and even more. That's a London squirrel, by the way. And most of the time, or at least, well, 1 or 3 times, it actually sees a fox squirrel here, so it knows it's a squirrel. But in the other cases, it thinks it's a hen. I don't know, this fat black one. I've been told it only exists in Stewtown in New York. That's the only place where it exists. I don't know if it's true. Like the fat, chubby one, and the final one, that's a hen, rather, because it probably hasn't been trained to recognize that hen. And I'm showing you this because it's entertaining, but I'm also showing you this because this is a pre-trained thing on just standard images, showing you this to show you how powerful it is. It has never seen a squirrel like this, and has never seen a squirrel like this, and it hasn't seen the cat of my friend, but still knows it's a cat. And the beagle thing, it also knows it's a beagle. And it's pre-trained, you just download it. Good. Just because it was like mentioned in the abstract, there is a totally different kind of networks as well, like recurrent neural networks. And what you've seen before is that information has been fed like just in one direction so far. That's why it's called feed-forward networks that you saw so far. But for certain other things, that's just not sufficient, especially for kinds of tasks where you have to do something with sequences of things. And that's typically the case with text processing. And because, oh no, I can't start it, right? Because, oh no, I was smart, I preloaded it. That was pretty good. So this is a thing using recurrent neural networks, in that case, long short-term memory network, LSTMs, that can like remember some of the inputs that it saw before. And what they did is they used the, how's the name of that video movie database? IMDb. And you get a description from people and you also get a rating. Like, is it a good movie or not? And then they trained a network with it that can, now when I type something, it can tell me, is it a good review or is it a bad one? And that's very important for some companies because they want to like scan Twitter, and every time someone says like Daimler-Benz is a shitty company, they want to see that and then react to it. So like I think it's called sentiment analysis. That's something that's actually also interesting. Quick, give me a review, a good one or a bad one. Just what should I type? Help me. Sorry? No, I have to write the review, not the title of a movie. An actual review. It sucks. So I type it sucks, and now the percentage that's actually a good review is 38. It's quite high, I would say, giving that review, but it's also very short text, but it sure knows it's negative. It sucks, and then it also sees what is the negative word? It sucks. It was so boring. How do you spell boring? Is that correct? Boring. Oh, okay. Now it gets really bad. So, and this is actually, as I said, this has been trained on the data set, and what is important is that the sequence, like it's like how the words are put together, actually is important. I think it doesn't work well with negations. So if I put something like, it still should work, but it doesn't. It does not suck. It was not boring. It still doesn't like get it. But I think that is the hardest part. And you see, it's probably not production ready. And but well, it's not so easy. So I think we are out of time. And actually, I'm very surprised that I could show you what I wanted to show you. I think.